won't start. So my name is Dmitry Petrashko. I'm a doctoral student in EPFL. For last year, I've been working on ScalaBlitz, also new both parallel sequential collections for Scala, and the second thing I was working on is Dotty compiler. So today I'm going to present to you how you can make your Scala applications using sequential collections faster with a single word. So I will start with showing you the differences between Scala and Java collections in a simple example. Then I will proceed with telling you what stops Scala collections from being as fast as Java collections. Then I'll share you several observations that I got from implementing Scala collection operations using macros. Those are about what is the bytecode size, which was one of the potential problems with it, and what's the interop with specialization. Then I show you a simple example how you can use optimize in practice, and then I end up with the supported collections and the list of speedups for them. After it, I will present you the future work that's the current research done. So Scala already has its own collections in place, and for most of things you can imagine, you can get the collection that just recite the same job. Because of this, you have a pretty lot of standard collections in Scala. If you think that it's a hierarchy of Scala collections, actually you're not that right. It's hierarchy of immutable Scala collections. Well, if you talk about the whole hierarchy of collections, you need to collect this graph with this one, those immutable collections. From just the side of this graph, you can see that the Scala collections are pretty complex. They try to give you both things at the same time. They try to give you quite a convenient API to use from the user's perspective and quite decent performance. While in the first thing, I would say that they actually do pretty good stuff. They give you a lot of operations that are convenient to use in your everyday life, that simplify your bytecode both in terms of writing it and reading it. In the second part, there is indeed a place for improvement. Let's have a look on it on a simple example. So we want to compare how would you write the implementation of the function that computes an average value of an integer array in Java and in Scala. In Java, because all the collections are only about storage, we will do it by hand. You will just use this collection as storage. You will iterate over it, accumulating the result of the sum in order to compute an average. And then you will divide this result to the length of the collection. In Scala world, you have a lot of helper functions. In this example, you can either use a reduce function or a sum function, and this will simplify your life a lot. Already from this example, you can see that Scala collections are a lot more convenient to use. So if you want to use average function several times, in Java, you will probably introduce a helper function just for this simple goal. While in Scala, the original implementation is itself a one-liner. So in some cases, you don't want to introduce new notion, the helper function, and you will just use it run this, write this one-liner twice. But this comes in some cost. If you will try to measure how much time does it take to run those two functions for a 50 billion elements array, you will see such numbers. So actually, in this particular example, Scala collections are around 32 times slower than Java ones. So now let's have a quick look on why. So if you'll have a look what does Java do in this particular example, you'll see that you'll have a simple cycle. The cycle contains a range check, then you add the value to the accumulator, and then you increment the index that you're using to iterate over array. If you have a more close look, you'll actually see that all those operations are indeed required. Because you're not tuning for a particular size of a collection, you actually need to maintain index. You need to do those range checks. And because you want to produce a result, you actually need to do addition. So comparing with the amount of work that's required and the result, you can see that this is a good baseline. And if you can even try to implement the same in assembly or C++, you'll see that the speed will be the same. It will take you around 20 milliseconds to compute the sum of the array without using some vector instructions. So now let's have a look what actually Scala does in this example, though that it takes here 33 times more to achieve the same result. So you're using helper function reduce here. This is the only thing in this implementation that takes time, that depends on the size of the collection you're iterating over. The reduce itself on a bytecode level looks similar to this. So you can see that inside the reduce there is a call for each. So reduce itself is implemented in terms of for each. And in order to analyze the performance of the reduce, we need to see the interaction between those. So here are those implementations. So you can, now I will try to follow you through those implementations just to see what does the cycle contain of in this Scala case. So cycle starts inside the for each. When you have the range check to check that you're not out of the collections already, then you get the element from the collection, underlying collection one, in this case array. Because you're already inside the collections library, and collections library is generic one, you need to pass this value not as a primitive integer, but as an object. So you will box this integer to an object. And then you will push this element to the helper function that was created by reduce in order to create this computation. After it, you will have dynamic dispatch just to check, to dispatch to which function are you actually putting this. Because you have the same function all the time, actually this dynamic dispatch will be almost for free because it will be in line by the JVM. Then you'll have this predicate check. You can also say that this is almost for free because in most cases JVM is smart enough to reorder instructions and run it without even jump. And then you'll have the dynamic dispatch that's due to the function you're passing as a reduce one, and here you'll have the full-fledged dispatch. And only then you will have the addition that you've been passing at the reducer argument. But in order to return the result from this addition, because you're once again in the generic collections framework, you will need to box it. So now you'll have the boxing as a result of your addition, just to be able to pass it as a result to the reduce. And then you'll have the increment that's inside the for each in order to continue with the next iteration. So if you'll just compare amount of work that's being done by Scala in Java, you can see that Scala pays a lot of overhead due to it being able to perform this operation in generic case. From my practical measurements, I can say that in most cases, single element allocation or boxing costs you around the same as 4 dynamic dispatches or summing of 15 integers. So all those boxing and dynamic dispatches actually, in this particular example, cost you more than the operation you were going to perform. So the short question is how we can fix it. One way is to reinvent new collections library and throw the old collections away and say that everybody should start to do the new one, but I would say that there is a better solution for it. As I told you, Scala Collections has a wonderful API, and I don't want you to stop using it because it actually gives you great developer experience. The way around would be to use such magic as optimize. So there is a single word that you can write and you'll get to the same performance baseline. So let me show you how it works. In order to show it to you, I'll need you to go give you a bit of history, but before I go to it, the question is whether the Scala collections are that bad. So in most, actually the example I showed you is a specific example that hurts the Scala into its weakest point. So in the Java example, you always have unboxed operations. And the operation you've had is the fastest one that JVM can ever perform, this addition of integers. While in Scala, you'll have boxing, dynamic dispatch, and so on. Actually, in most real-time applications, you perform operations on the box collections by its own because those are not primitives. And in real-time, in real-world examples such as PageRank, the speed up that you can achieve by writing in Java code or using optimized macro is not that big. This is about 40% in real life. But this is still a place for improvement. So before we start of saying how it's work, I want to show you how much actually you can improve here. So as was seen in what Scala does, the question is how much work is done that you're not asked Scala actually to do. The thing you asked Scala to do is the addition of the elements. And the less time does the operation require itself, the more percentage of time is spent by Scala on performing the operations that are just to overhead of iterating over the collection itself and the dispatches. Let me illustrate it for you on several operations. So if you perform the summing of the range, it's a very fast operation to perform because range doesn't actually maintain a huge memory footprint. It maintains only several integers inside. Then the time of summing the integers itself for a 50 billion integer range is around 4.5 milliseconds. But in order to iterate over this range itself, you will also need to pay the price of 2 milliseconds. But because you're passing a generic function as a reduce argument, you will need to box every integer you're going to sum and box every return of this value of this summing of two consecutive integers. That will cost you a lot more than the summing and so on. It's not that bad an example of the arrays because the iteration itself costs you a bit more. And so that the overheads in the example of the range is more visible to the example of arrays. If you're going to perform the operation that's actually do more work, like mapping, because they produce a collection as a result, the amount of work per single element that you're indeed going to conduct is a lot bigger. So that's the operation time itself increases to a high degree, and the percentage that is replaced for improvement decreases. And if you're going to perform some highly costly operations like mathematical operations or big operations on data, the percentage is even bigger. The same can be illustrated on a simple graph. So here, as red, you can see the invocation overhead. It's almost the same for most collections because almost all the examples I've shown you, the overhead is due to boxing. Iteration for ranges is the smallest one, while for the arrays is the same. The thing that you are actually interested in this yellow part. The bigger is yellow part, the more time Scala collections has spent actually performing the operation you requested. So we can say that the range reduce in this example is one of the least efficient operations. Implementations of this operation is one of the least efficient because most of the time it does its own job, not the one you requested it for. While the array map for a case of that you pass in it a slow function is not that bad, but still you can try to make it almost 2 times faster. So once again, coming back to the point I wanted to make in this, is that the faster the operation is that you're going to perform on the element, the more prone you're to this speed up. So in case you're trying to perform the operation that requires only a little amount of work for every element of a collection, actually Scala collections are not that good for that task. So let's try to improve it in this case. The project ScalaBlitz started a year ago. Under supervision of the Alex Prokopets and cooperation with him, we tried to create new Scala parallel collections that had a better API and had a better performance. In terms of API, I can illustrate it for you in a simple example. So Scala already has its own parallel collections. And there are some types of code that you can write using parallel collections that will compile and run, but it probably shouldn't. Let's have a look at this example. So you have a list, and just the API of these collections allows you to say that this list will become a parallel list, kind of, and then you will be able to perform both scan left and fold right one after another. If you don't know that good what it will run in the runtime, let me show you. So actually, list is not a parallel collection. You can't conduct any operation in parallel on it. And when you invoke .par on it, the list will get copied and you'll get a par vector. So now you will pay the price of linear copying all the collection just to start your parallel operation in the first place. Then you ask the parallel collection framer to perform the operation scan left. If you have a look of how is scan left defined, scan left will return you the result of applying the operator going from left to right. So this operation, it inherently defined order in which operation should be performed. And this order is inherently sequential. This operation can't be applied in random locations by different threads. It can be only applied in left to right, so that the second thread can in no way help the first thread because there is only one element of job that can be done in every moment. So the next operation you wanted to perform is fold right. So now, instead of going from left to right, you go from right to left, getting instead of collection a single element. Once again, you have the operation that inherently defines order in which you're going to compute the result, and this is no way able to be parallelized. It's not only a problem on Scala parallel collections, actually. You can do the same with Scala views. And because those operations actually require you to traverse the collection in different order, there is no way to implement this efficiently, neither in parallel collection or in views. So one can say that the all Scala collections, both parallel, both sequential and views, share the same API as advantage. But in some case, this advantage actually will hit you, because you actually expect that if this code compiles, that it will run the way it's expected to run. But such code can never run, and I would argue that it shouldn't compile just because of this. So it's the question, how does ScalaBlitz, what's the difference between ScalaBlitz parallel collections and Scala parallel collections in terms of API, because all the operations that are in ScalaBlitz are indeed performed efficiently. If you want to perform some inefficient operation, you need to explicitly get the sequential version and perform it explicitly sequential. So in terms of performance, the performance question can be illustrated by this simple example. So if you had the different implementations of ranges and you want to apply reduce function and get the sum. So the par range, the second column, here is the standard Scala collections. So if you try to apply reduction function, such reduction function on Scala parallel ranges, you will actually get the running time 20 times slower than the sequential version. Is due to amount that's for parallel collection, amount of overhead per single element is a lot bigger than for sequential collections. And the problem with overhead that I showed you in the previous diagrams is a lot huger. So in order to solve this problem, we implemented ScalaBlitz that has low overhead per element being a parallel collection. But it came up that we not only have beaten the parallel collections, but we also have beaten the sequential ones. So trying to implement the parallel collections, we actually were able to beat the sequential collections on a single core. So you can see that we're actually, on this example, 20 times faster than the sequential collections on a single core, and we've got wonderful scaling scheme in this example. So the more cores you get, the faster you are. Seeing these graphs, we understood that we can easily bring these performance advantages to sequential collections, and this can be easily implemented without people actually needing to rewrite their code. So we've implemented this macro block called optimize that uses macros to understand which code did you write and rewrite it using the ScalaBlitz operation. It means that you don't need to rewrite your code. You don't need to start using different collections. You can continue to use convenient for your API, and by adding a single word before the definition of function optimize, you can get all these performance advantages. But once again, because this is a macro, there is a slight fear that we had originally that the single line that's optimization of the single reduction will expand as a macro to several hundreds of lines. So we were afraid that the bytecode size will just blow up after you will try to use several macro operations in the end. But it came up in practice that in reality it won't. Because when you try to run such code in Scala, if you'll just compile it directly, you'll have a closure here. And this closure is an anonymous function that will require compiler to generate a special class for it to pass this function inside the collection. But in our case, we're inlining all those closures so that we're creating less classes, less bytecode. In the end, the bytecode footprint is actually smaller in most cases. In other cases, it's just comparable. So in the example I just showed you, we actually even create the reduction of the bytecode size. So the other thing that I wanted to share about observations while developing it is that some Scala collections are not specialized. So Scala ranges save integers, and they always store these integers and it is integers. Scala arrays are actually Java arrays, so they store integers as primitives, doubles as primitives, booleans as primitives. Well, if you try to use Scala lists aren't specialized. They will always incur boxing just due to you trying to save something in it. And if you try to optimize list by using the same approach, you will have no win, because you will already pay the cost of unboxing and dynamic dispatch just because of this genericity. So let me illustrate it to you in the similar way illustrated comparison with Java collections before. So let's have a look on the count example. So we're currently looking how the count is implemented for lists. So the count function the count function, given the predicate that tests every element, returns you how many elements fulfill this predicate. In order to implement it, it relies on for each that's defined in the optimized sequence. And you'll have similar example as previous. So first you'll have the range check that you're not out of the collection here, because the list is this linearizable collection that is implemented in this way because it's faster. Now you'll have dynamic dispatch that goes back to count. The first dynamic dispatch is almost free, this one, but the second one here is not, because you're passing a generic function out of scope, so Gevent isn't smart enough to inline it. Then you'll have unboxing of elements. Because you had original element boxed, you'll now pass it to function as a boxed one. But because function itself, if you're going on the functions of integer, will do something reasonable with this integer, for example, compare it. In order to compare it, it will unbox this integer. So you're still paying this price. Then it will do the predicate check inside your methods that you passed, and then it will actually increment the counter. If you'll try to rewrite the same in ScalaBlitz, the only difference is that you will inline the method. For example, if you're trying to check how many elements of the collection of integer are positive, you'll have code similar to this generated by ScalaBlitz. So here you'll have the same. You'll have range check. Now you'll have unboxing of element not inside the dynamic dispatch, but before it. It doesn't make big difference because most time is still consumed by just converting one into another. So win is not that clear. And it's ended up that the only difference is that previously you had unboxing after dynamic dispatch. Now you had unboxing just in place. So there is a potential there can be potential improvement of implementing such operation using macros, but it can only be done efficiently after we have the storage of Scala collections already specialized. There is a project that's aimed on the improving Scala specialization called Scala mini boxing. As far as I know, it will be presented tomorrow by Vlad. So if you're interested in this, I expect a wonderful talk there. There are several caveats of this project. First one of the ScalaBlitz is sequential collections. First one, that's if you use an optimized block, as was shown in the previous slide, it will actually generate a lot of macro-generated code that has only small something to do with the code you originally written. So it's hard to debug if you'll try to debug it in runtime. But it's not that big problem because we're following the guarantees of Scala collections, and I'm not sure if anybody of you tried to debug Scala collections internally. It's not that simple task. So in both cases, you're trying to go into the dark wood. The other problem with that, because we rewrite code, also the stack traces change, the runtime profile change. So in order to use profiler with ScalaBlitz, we will probably need to see that the code that's generated, so we will need to investigate either the bytecode or the trees. Also, because ScalaBlitz originates from the parallel collection, for every of your operation invocations, it will create several simple objects just to pass them at the container for methods, and for very tiny collections like range of 5 elements, it actually will cost you more than the operation itself. So in most cases, ScalaBlitz as fast as the sequential collections for collections of around 10-20 elements, and then it gives you a clear win. And the other restriction is that for now there is no custom build front support in most ScalaBlitz in the optimized block, but it's just because I didn't have time to implement it yet. So now I'll have a slide that illustrates which collections do we support and speed up for them. So as I illustrated previously, the speed up highly depends on the operations you're actually performing. So those speed ups are the speed ups for the fastest operations you can get. So in case of reduction, it's just summing all of all the collection. If you're performing an operation that is inherently slow, you probably won't get such big numbers. So in case of the unboxed collections like ranges and arrays, you have a huge speed ups. So it's very easy to get a 20 times speed up if you're doing some operations on arrays and ranges by just putting in an optimized block. In case of hash maps and hash sets, both mutable and immutable ones, as I said previously, have this problem of boxing. But because we know how they're internally implemented, we're able to, even in this case, bring you the good speed up. In case of lists, when you're performing the operation that has an intermediate result that we can maintain as an unboxed one, like inside the reduce or inside the sum, we can get you a clear advantage. But if you're trying to create a collection that itself requires boxing, most of time is just consumed by passing it from one boxed state to another that still is in place. Here in some locations you can see this unsupported and you can have a question, what does it mean? By unsupported inside the optimized block, it simply means that optimized block won't rewrite these operations. You can still perform them, but they won't be just conducted by ScalaBlitz. So the future work that's potentially can end up in optimized block is operation fusion and deforestation. Let me illustrate you operation fusion on the simple example. So imagine you have one collection. For example, you have a list of integers, and you want to perform multiple operations over the same collection. Over the same collections, for example, you want to compute the minimum element, the maximum element, and the average element. In this example, you have a list, so in order to compute an average element, you need to apply two operations that take linear time. So summing all the elements of it and getting the result, and getting the size of list. So in order to just run this operation using normal Scala collections, you will need to perform 4 independent iterations over the list. One to get the sum, one to get the size, one to get the minimum, and one to get the maximum. Actually, if you write this code by hand, you can perform all those operations together, having a single iteration and actually having 4 times less running time. And potentially, using quite a smart analysis, it can be done by optimized block automatically. We're researching this problem. The second improvement that we can potentially bring is that's deforestation. So imagine you have several operations doing in the collections, and these operations create intermediate collections on their own. For example, you have collection of people, and you want to filter who of those people is male, and then get the minimal age of the males. So you first map over those people, and then you compute min. So in this example, you will actually create 2 intermediate collections. First, the result of filtering, the second is the result of mapping. Those collections are created just in order to be consumed by the next operation. So during quite a smart analysis, you can try to use stream-like pipelining and reduce memory footprint in this example to up to 3 times. So this is the idea. Now let me show you a quick illustration how you can try to use ScalaBlitz on simple examples. So here I have the Scala console, SBT console. And let me show you how this works in a simple example. So I have an import here that imports the optimizer. It's the only import you additionally need. And then let's have a small comparison. So I have the measure function implemented here that allows to measure how much time does operation take. And now we can define some collection. For example, we have the collection, the normal range of 1 billion integers. And we want to see how much does it take to compute the sum of this collection using reduce, for example. So using standard Scala collection, it will take you 34 milliseconds for warm-up, and then you'll have the 10 milliseconds after warm-up. Then, if you'll try to optimize it by putting a single word here, you'll have the running time that's more than half millisecond. So in this example, you straightforwardly get the speed up of 25 times. Let me show you an example for arrays. For example, we use the same collection. And for example, we now will, instead of using the reduce function, we'll map this collection. So in case of Scala, we've got running time around 19 milliseconds, and after we're mapping it should stay more or less the same. Because Scala creates a lot of garbage here, you don't have a stable value because you have multiple GCs. And in case of optimize, we will see reduction of time. So we can see that in this example, it takes, once again, less than 1 millisecond to perform the same operation. So also we have a speed up of around 30 times. So that's actually all I wanted to present. If you have any questions, feel free to ask. Please.
I have one question really. Is it fair to say that these are basically essentially a bunch of optimizations that are based on heuristic code analysis? Like, this is the collection you use, this is how you use it, this is the pattern, we support this, so we optimize this via a certain specialized code path?
The thing that's currently supported by the optimized block, I would say no, because actually the thing that's done is just using the knowledge of the types that are you using in your particular location. So if you're performing operations of integers, the generated code will just perform it on integers. It won't support any other type because you didn't ask it for. And it will only allow you to perform this operation with the particular collection type that you see there statically. So I would say that it's not in any way heuristic, it's just tuning the collection operations for your particular use case that you requested it for.
The follow-up question is it conceptually possible to generify the solution and fold it into an optimization phase within the compiler itself?
So there's the idea of making the compiler smaller. And the advantage of ScalaBlitz that it's actually an optimizer that's not part of the compiler. So actually, I would say that while potentially there is a place for it, maybe it's a better idea to just leave it out because it can develop independently from Scala, and it can develop independently for Scala compiler and Scala collections, and so this way it's a lot easier to manage. So there is a problem that Scala compiler and Scala collections and generally Scala deployment is huge, and you want to modularize it. So in this sense, it's already an independent module that works great. So from Scala itself, it requires an API, those Scala macros. And Eugene has done a pretty good job on implementing it. Please? So all this is performed in compilation time, all these transformations. Yeah, so the current implementation of optimize is actually a recursive macro. So it tries to optimize the code as much as it can during the first calling of it, but due to the way how Scala macros work, in some cases it will see untyped trees, and then it will expand on its own. In the worst cases, it can take up to square time depending on the call size, but in order to have this example, you need to explicitly write the code that's the worst case for it. In most cases, it's pretty fast. Please.
So you talk about bytecode size in terms of total bytecode size.
Yeah.
In practice, one of the things I would worry about with this is hitting the 64K bytecode per method limit, the JVM.
Mm-hmm. So actually, speaking of this, ScalaBlitz on its own, in most cases, generates multiple methods. So you will probably not hit this problem just because of ScalaBlitz, because instead of creating one huge method, it will actually break your code to smaller ones. That JVM is a lot better in optimization. Actually, if you'll have a look on our website, we have several examples in which we actually outperform handwritten Java code. We're 5–10% faster. I believe it's just because we're actually creating the code that's more friendly for GVM to optimize than a simple while cycle, because we have broken it into smaller parts. Yes, please.
A while ago, you said that you were looking into removing the runtime support from ScalaBlitz to let it run on Scala.js unchanged. Is that happening, or?
So as far as I remember the question, the answer I gave was not about the runtime support, but about multi-threading support, because that's not supported by Scala.js.
Yeah, I guess the more general question is, since optimized macro has a lot of speed up for single-threaded code, could be used on Scala.js without having all the multi-threading?
So I believe because you're speaking in Scala.js, you don't. If you have the code that doesn't run, but doesn't and doesn't compile, if it would be run, you don't have problems. So here you'll have actually in ScalaBlitz you'll have the sequential scheduler that knows nothing about multi-threading, and it should be safe to use. But if you'll try to explicitly say multi-threaded environment, then you probably will have runtime failure. But I haven't tried in Scala.js. Yes, please. Yes, you can nest one optimize inside another. So while theoretically it is, there is no guarantee in which order macros will expand. So there is a problem that making it work reliable is not that reliable. So I would say it's easier to leave it when it works always. Okay. Any more questions?
As I see from the presentation, the main profit is in array. But array is a really special case in Scala. Everybody knows about it. And the speed up in other collections like maps, sets, and lists is not that good. So maybe put a bit more effort into array instead.
So speaking of the arrays, it's not specific to arrays in terms of performance. It's specific to array that's in case of arrays, you already have the biggest bottleneck that's specialization of collection already fixed for us. In case of hash maps, you can see that for reduce, we're also able to get a substantial speed up. But I would argue that for list speed up of 1.5 types is also quite a substantial one. But I would say that this graph, this picture should tell that there, before doing optimizations in the whole scale of the collection, the problem of specializing collection should be solved first. Mm-hmm.
Well, array is always a special case because of those wrappers, array ops, and so on.
Mm-hmm. Here, most ranges are around 5% in both sides. So it's actually performance of ScalaBlitz is a lot more stable than the performance of standard Scala collections. So you get less de-optimizations done by the GVM in runtime, and you get a lot stable performance in the overall. Yes, yes, yes. So then the biggest bottleneck that's present now that I'm not solving will be out, and you should be able to get similar speedups for lists.
And so how does the picture look for non-primitive types? Is there a significant speedup?
So if you run some operations for non-primitive types, the most speedup actually comes from the enlargement of the horizon of the optimization by the GVM. Then it's very specific to what you actually do. But the trick is that in this case, GVM can do a lot better job optimizing your code. Actually, JVM is really pretty much bad in optimizing functional libraries because it's not used to somebody passing functions from different locations to the same hot place. So Scala collections are used over all your program, and over all your program you pass different arguments to result. And this ends up as a megamorphic call, so JVM doesn't inline, it doesn't optimize it almost at all. And if this will be implemented using macros, JVM will inline it because it's not its job anymore, and then it will have the larger optimization go horizon and other JVM optimizations such as escape analysis, on stack allocation will kick in. It will be faster just because of this. Yes, those numbers are for primitives. Do those collections have higher order functions, such as reduce, map, fold? Then I believe it's you can try to extend them using this approach, but it's once again you're extending it, you're not optimizing it. You're adding the new operation that weren't there before. Yes, pretty much. Any more questions? Please. Mm-hmm. To what, please? So mostly my work is about operation fusion. So with super compilation, it's not that my part. But if you have a precise, more concise question, maybe I can try to answer. Yeah, kind of. In some understanding, yeah, that's true. Any more questions? Thank you for your time.